Hello everyone, welcome to another ACE Computer Vision Spotlight session. My name is Mahdi Biparwa. I'm an R&D engineer at Sunnybrook Research Institute and a computer vision stream owner here at ACE. This is my pleasure to host another great talk today. The title of the talk is Set Constraint Temporal Transformer for Set Supervised Action Segmentation. This paper is presented at CVPR in 2020. I'm very excited to host the author of the paper, Mr. Mohsen Fayyaz, in this amazing session. Mohsen is a PhD candidate at the University of Bonn. Um, um, he is in the computer vision group working with Professor Dr. Jürgen Gall, and he's working on video understanding, action recognition, and temporal action segmentation. He was co-organizing and program chair of ICCV 2019 workshop and CVPR 2020 tutorial on holistic video understanding. He's also a reviewer for NeurIPS, ICLR, um, um, A, AAAI, and international journals, including IEEE, TPAMI, and IEEE. Without further ado, um, let me welcome Mohsen to our session. Mohsen, please take it away.
Hi everybody, I'm Mohsen and today I'm going to present our latest work in CPR 2020 named Set Constraint Temporal Transformer for Set Supervised Action Segmentation. This is a joint project by me and my professor Jürgen Gall. So let's go. We are going to talk about understanding untrimmed videos, not just some trimmed videos, some short video clips. By untrimmed videos, what do we mean by untrimmed videos? So an untrimmed video is something like this video that it's somehow about 1 minute and 29 seconds, and it encompasses lots of actions and activities going on. And you can see that if we want to understand what's going on exactly in this video, we may say, okay, there is a main activity going on here, but there are lots of sub activities, sub actions happening, and there are lots of objects involved. So I'm not going to watch this video until the end of it. Definitely, they're preparing something for the breakfast. So how can we, let me switch to the full screen. Okay. So for understanding an untrimmed video, one thing we can do is to do the temporal action segmentation. What do we mean by temporal action segmentation? For example, we have a video here, and we have a video here, and we can see that the video has lots of frames. For example, in the first section of the frames, the person is doing the action of pour oil, and the next one, she's doing cracking the egg. After that, stirring the egg, frying the egg, and then put the egg to the plate. So the input of the video is the set of this ordered set of sequence of the frames we have. We call it X. And the actions we have in the video are something like that. So for each frame, we have a label here. We want to describe every frame of the video. So we want to temporally segment the video. And the overall action of this video is preparing Friday. Lots of state-of-the-art video understanding action recognition works going on today are mostly for example, the 3D CNN, something like slow fast, X3D, or 2Stream networks are mostly focusing on trimmed short video understanding for action recognition in trimmed videos. And for example, if this video was a short video, for example, something like 10-second video. It was a trimmed video. And the label of the action was prepare fried egg. Then this type of 3D networks are mostly focusing on solving such problems. But for untrimmed video understanding, we mostly face real life problems that we have a long video, it's not trimmed. It may consist lots of actions, as you can see here, and it may also have some main action or may not have some main action. And we want to understand what's going on exactly in each section of the video. For example, for websites like YouTube, people upload lots of videos, untrimmed videos to the website. And so if you have a machine learning algorithm which wants to just annotate the videos, tag the videos, and classifies them and using those annotations and tags for our search engines. So we need to know what's going on in every frames of the video. And if we have a long video, if it's a 10-hour video, if it's, I don't know, even 10 minutes video, we need to know what is going exactly in every section of the video. So the first solution comes to mind is that using full supervision for training our deep learning models to be able to temporally segment the untrimmed videos for us. For example, if we have a video which has this T frames, we call them T frames X. For the supervision, we have the Y, which we have the label for every frame. So first, let's see that what are related works. So by related works, I'm just picking some more recent related works. Definitely, there are lots of related works which are working in this area on untrimmed video understanding. So I'm just picking some of them so we can fit all of them in this session today. So for fully supervised video segmentation, there is a paper called MSTCN in CPR 2019. That's also from our group. We will first go through this paper to see how people solve it if we have the full supervision for the videos. And afterward, we will go for a paper which is using weak supervision, which is called, for example, in that set of problems, we have the weak supervision of the ordered sequences of the actions. I will also explain it how it is. And afterward, we will go to the final work that we have presented in CPR 2020. So for fully supervised temporal action segmentation, one of the state-of-the-art methods for which was presented in CPR 2019 was this MSTCM paper. I'm going to briefly explain it because today we are mostly focusing on the weakly supervised methods. So what do they do in this in this paper? The idea is that they get the input. So we call the input X, the frames. So, and then they also have the labels. So they have an architecture which they feed in the data. The input data is fed to the network, and then they also have the labels, and then they train it like just normal deep learning methods. But there is a point here. So we said that the videos are untrimmed. So you cannot feed all of the frames on the GPU memory and just feed it to the network and expect it to predict the action labels of every frames, and then we can backpropagate through it. It's not that easy. So what people do now is that they use some pre-trained 3D networks or some other feature extraction techniques. Actually, nowadays, everyone uses deep learning methods. And they extract, they represent the frames, they extract the feature of each frame, and then they use this represented features as the input to their model. For example, in this work, they have used i3D and also, which is a deep learning method for feature representation, which is a deep learning to a stream deep network, which is pre-trained on kinetics. They use it for extracting the features. They have also tried the IDT, improved dense trajectory technique, which is a not non-deep learning method. So the point is that they are somehow performing the same. Their results they have reported in the paper. So their method is not heavily relied on these represented features. And when they have the features, they call this set of the features of the frames X. They feed it into their net. So what is the architecture they are using here? The architecture is actually some states of a 1D convolutional network. And the 1D convolution network is followed after the wavenet, which was one of the state-of-the-art architectures for speech for processing the audio signals for speech recognition, etc. So they have a wavenet here, and they also have another wavenet here, but it is not exactly wavenet; it's a modified version of wavenet. And the question is that why it's good here? Why this 1D convolution is one of the perfect models for this fully supervised action segmentation. The point is that they are using the dilated convolution, dilated 1D convolutions in this architecture. And as you can see, because of using this dilation, you can see it here in every layers of the architecture. We will have really variant sizes of temporal receptive field over the input at every level of this wavenet, level of this 1D convolution. And they're using multiple stages of this 1D convolution, and they are getting a state-of-the-art results because of having that different sizes of receptive fields in every level of the network, so they can capture long dependencies or short dependencies between the temporal features they get. So we talked about the fully supervised
Mohsen, before
on-chip.
getting further, I have a question.
Yeah,
Do they save the features after the um, I3D, for instance, network? So they have two-stage processing, right? So at the first stage, they save all the feature embedding across the
yeah,
long video, and then once they have them, they use the second stage. Is that correct?
yeah, yeah.
Okay.
That's the offline processing they are doing, but the point is that they can easily change it to online during the inference. Because the point is that if the GPU has enough memory
Yeah.
during the inference time, there's no constraint for it
Bottleneck.
because they just need to represent the features, and so it doesn't occupy lots of memory. Even if the memory is limited, you can use two GPUs. On one GPU, you can do the inference for a representation of the frames, and on the other GPU, you can have this processing here.
Mhm.
This
Okay.
architecture, the whole one, it doesn't really need lots of GPU memory, even during the training, because
Mhm.
we have some represented features, and the convolutions are 1D convolutions. So
Mhm.
here they're mostly focusing on this temporal relations between the frames, the represented frames. So it doesn't need lots of GPU memory.
Mhm. Yeah. Thank you.
And also there are some technique for if people want to train it end to end, but yeah, in this session we cannot cover it. We do not have enough time.
Yeah.
So one of the most important problems in temporal action segmentation is the supervision. This having supervision for every frames of long videos is super expensive. How come can we label every frames of a large untrimmed data set? We will have billions of frames, and we will need an army of annotators who can annotate all of these frames for us. So what is the solution here? One solution would be, definitely we will go for some weak supervision techniques, weakly supervised techniques. And one of the somehow popular weak supervisions that people are now working on is that transcript supervision or ordered sequence of actions. What is it? So we say we have this video we talked about. So we have this frames, X input is given. But for the actions, uh, in full supervision model, we had this Y. And the Y, for Y was the labels for every frame. However, in transcript supervision, we only have the ordered sequence of the actions. So what do we know in here? We know the actions, the order of actions happening, and the number of actions. For example, in this video, we know that the actions A has happened 2 times, and the first action was A. Afterward, B has happened, then C, D, E, F, and again A. So we know the order and we know the number. Just this. So definitely it would be really hard because we have bunch of frames. Maybe in some videos, for example, on breakfast dataset, which is used in this in our paper and even in this big supervised technique we are going to talk, and even in the fully supervised one, some videos have about 10,000 frames, and for the sequence we have as the label, we have maybe 5 or 6 labels there. The other problem is that for training such methods, even the fully supervised one, there is a high variety of frame size between the videos. Some videos have 500 frames, some videos have thousands frames, some videos have less than 100 frames. And the other problem in weak supervised methods is that the output of the network has also a high variancy, and also the size is really different compared to the input. For example, as I said, we have 10,000 frames, but as the output, we have maybe 6, 7, or 8 actions. And even for the videos, there are videos which have about 25 actions, or the transcript of the actions. The length of the transcript is about 25, 26, or even 30. And some videos have only 5 or 6 actions. So it is really a hard problem if you want to consider. Even, for example, in NLP, we have these sequence-to-sequence problems, but there we are translating some sentence from one language to another language. So the difference is not that high that we have here. So let's talk about one of the recent Wiki supervised techniques using the transcript called MuCon. This is a joint project with me and my colleague and our supervisor, Professor Gell. So what do we do here? As we said, we have the transcript. And the problem now is that it's not that easy to just having the frames as input and then having the labels as the output and then train the network. Say, yeah, that's how it is, and let the stochastic gradient descent work. No. So what do we do here? Again, we have the input. We again represent the frames as some features, and we call them X. For example, in this method, we use again I3D to be able to compare it to other methods. And we have an embedding, temporal embedding network here that is the same as the previous work we saw, which is a modified version of WaveNet. And now this is the hard part that we are going to tackle here. So we have the temporal embedding. We have somehow represented our features, and we are exploring some temporal relations, the long one, the short one, but we don't have the supervision. So what do? We say a video could be represented in 2 different ways. One way is like that we have the full supervision. So we say that for every frame, we can predict action probability. We call it Y here. And so we have this temporal representation here, which is the temporal embedding over the input features. We use our FC, which is some 1D convolution as a classifier. And it represents the Y for us. So the other way is that we can represent the video as some pairs of actions and the temporal length of that action. What do I mean by that? We can, for example, for a video, I can say this video has the action A1, and the length of this action is L1. And then the next action, for example, is A2, and the length is L2, and so on. So how can I get this representation? I have this segment network here, which is a variation of sequence to sequence network. So I ask this network to predict the sequence of actions for me. So here we will get the sequences of actions. A1, A2, etc. And also I ask it to estimate also a length for each of these actions. So I will get a sequence or the sequence of lenses here, estimated lenses. But what is our supervision? The only supervision we have here is A hat, which we said it is the sequences of the actions. So for this prediction, we have the supervision, and there is no problem for training. However, for this one and this one, we don't have any supervision. And this is the hard problem here, that we want to know the temporal lenses. Otherwise, we cannot segment it. So we use our mutual consistency loss here to be able to backpropagate from this A hat, which is this ordered sequence of the actions, over this prediction, over the length predictions, and over this temporal probability prediction. So how does MuCon work, this mutual consistency? We have some mask generation technique. We have introduced it in this paper. I'm not going to go through the details here, but you can approach me afterward. We are described in the paper. So what does this mask generation, differentiable mask generation do? Is that we have estimated the lenses. So our mask generation generates a mask based on this estimated length. So for example, a mask would be something like this, W1. As we know the order of the actions, we know this is the first action. So the position of this action, P1, would be 0. And we also know the L1. So this is 0, sorry. So the mask would be something like this. The first part is active, is 1, and the rest is 0. What is the second mask? So we know the P2. How do we know the P2? Since we know the P0 and we know the L1, so the P2 is accumulative sum of the previous estimated lenses. So P2 would be L1. And we also know the L2. So we can generate this mask. So it is deactivated for the previous part, for the previous action, and it is also active for this section and deactive for the rest. So what do these masks mean? For example, the first mask. We said that the L1 is for the first action. So we want this mask to somehow mask out the other action probabilities predicted in Y, and only let here to pass through. Why? Because we believe that, okay, if this is the first action and the length is this size, these action probabilities can pass through this mask. And we also do it for the other predicted actions and the lenses, as you can see. So what happens if I multiply this mask, I apply it over this y, this predicted actions probabilities. If I multiply this one to this one, I will get only action probabilities for the first action. And if I just normalize them and just take an average over them, I will get only one action probability as a tensor. And also if I do it for the rest of the actions, I will get A2, A3, etc. So what is this? This is the prediction of, this is a ordered sequence of the predicted actions. And since we have the A hat, I have also the supervision and the label. I can backpropagate through it, and I can train the model. And since the masks are differentiable, I will backpropagate to Y and also to the estimated lenses L. So if I go back to the network, I can see that I can also backpropagate through here, and through here. So I can train this model end to end, and we will use this as a extra supervision, so we can train it, and yeah,
So I have a
problem is solved.
question. Do you
Yeah,
so you generate the masks based on the predicted length, right?
yeah,
So basically what you do, you have the predicted set of actions and then corresponding length for each one of the actions, and then you
yeah,
generate the masks, and then you try to force the network to be as consistent as possible between the
exactly,
mask and the
exactly,
segmentation, right? The
yeah,
predicted segmentation.
exactly,
Okay.
exactly. The
So it's
point is
sort of
that
a sense of self-supervision between different parts.
exactly that's why we have these two type of presentations. We use it as we use this type of two type of different representation. They should be consistent because they are representing one thing. They are representing the z, and the z is representing the x. So the consistency is this self supervision we are using here.
Great.
Okay, and so now let's go to the next part. So we said that as a weak supervision, we use these ordered sequences of actions. And definitely it's cheaper to have it compared to the full supervision. However, it's still a little bit rare because how can we get an ordered sequence of actions for every video? Is it freely available? Some may say yes, you can use the transcript of the movies and extract some keywords from it using some NLP techniques, and then you will have these ordered sequences. However, one easier weak supervision, which is somehow really freely available over the web, is just set of actions. What do we mean by set of actions? For again, we have the video, we have the input frames. However, for the actions, we don't know the orders and we don't know the number. So we know the action A has happened. How many times? We don't know. We watched order, we don't know. So how can we get this type of supervision from the web really? You can use the tags people provide when they are uploading their video to the social media or wherever. They're describing their video with some tags, and you can use the tags as a source of supervision. So the problem, however, is a little bit more difficult compared to the previous one, because here we even don't know how many times the action has occurred in the video. As you can see, for example, A, we just have one, and we don't know the order. And it makes it really, really hard. So let's see how we have tackled it in our CPR paper. So we say that each video, we can describe it by having some temporal regions. It's like the previous work that we say we can explain, represent the video by just some temporal ordered temporal segments. That, for example, we say this region has the action A1 and the length L1, and also the other one, and so on. So the point is that in this work, we ask our model to estimate to divide the video to some temporal regions, we say co-temporal regions, and estimate the action probability and also the temporal lengths of the actions for each of these regions. But still, we don't have the supervision because we don't know the order and we don't know the number of the actions. But let's see how we can solve it. So this is somehow for this method. We say again, we have the X, we use I3D to represent the frames. And we say, yeah, X is the represented frames. Again, we say we have a temporal embedding network. Like the previous work, we use a modified version. It's a little bit also different to the previous work and to the fully supervised, but still there are a modification of something like WaveNet. And then we get this temporal embedding Z. However, we add another network on top, which we call it temporal region estimator network. So this one is also similar to a WaveNet. It has some 1D convolutions. It downsamples the Z furthermore to Z prime. And for Z prime, we say that it has some representations for the temporal regions we expect to have for video. And then we have two different networks, which both of them are 1D convolutions, but one of them is a classifier, this one, which predicts the action probabilities for us. Another one predicts the temporal action lengths for us.
For each region?
Yes, for each region. And finally, we will get these action probabilities, set of action probabilities, and also this ordered set of this estimated lengths. So how can we still, the problem is that how can we solve it? Because we don't have the supervision. Yeah. So we say, okay, we have divided the video to k temporal regions. We have also predicted some action probabilities and temporal action lengths for these regions, which we call them A and L. So we have them. However, we still don't have a representation that we can use it alongside with our supervision, which is set of action probabilities. So what we do here, we have a region upsampling module, which is also another contribution of this work, which is differentiable. So this upsampling module upsamples A with respect to the L. So how does it work? For example, if in A we have, for example, we have A1, A2, and let's say A3 and AK, and also we have the lenses. Oh, sorry. Okay. But this upsampling, it's not as simple interpolation technique. It upsamples so that in Y we will have this size is L1, and all of this region is A1, and for example this is O2, and this is A2, and so on. So this would be the Y for us. So we upsample again to get back to the same size as x. X is also x is d by t. T by d. D is the dimension of our feature representation, and y is t by c. And c is the number of classes. So now we have a representation. We have action probabilities for every frames, but we still can't use it because we just have the setup action. So here is explanation how this differentiable upsampling works. It's a little bit complicated for this session. I just leave it out, but I put it in the slide. So if later you can go through it to see how it works. And also we have explained it in the paper, and I'm going to release also the code, and you can also use the code. Anyway, so we said that we have predicted action probabilities for every frame, but we just have set of actions as the supervision. So how can we use it? First, let's say that what are the different losses of regularizers one can use when has a set of labels, and you want to use it over a ordered sequence of probabilities, such as y we have here. So definitely the easiest one would we call it set loss. So what we can do here is to apply a pooling over the predicted actions and say, yeah, we have this number of actions, so we know the classes, so we can apply the loss. It's really straightforward. Something is. Another one is that we can say that okay, we want to somehow enforce our model to just predict one action per each region, not predicting the multiple actions per each region. So this is another supervision. We have also just evaluated the effect of using these supervisions in the applications. And then another supervision is that we can say we have temporal consistency in video. And what do we mean by temporal consistency? We mean that the neighboring frames might have the same action probability. So it is more probable that the neighboring frames have the same action probabilities compared to the more far frames. So we also use a temporal consistency loss here. And then we also have a region length regularizer, which regularizes the lengths of each region. By regularizing, we mean that we somehow limit the variation of the region lengths, preventing the model to overestimate some regions, the length of some regions, just penalizing it to not predicting two different sizes. It somehow prevents the model to prefer to predict the longer temporal regions for the actions which are usually available in all of the training videos. So let's go to the most important part. The point here is that using all of these losses and regularizers, which are something common, people use some of them in some other works. We cannot train. We do not have any supervision for L, and definitely we cannot train FL. We only have this regularizer, but it's a regularizer. It's not a loss. So how can we train this part using our set of actions? Here we use our set constraint temporal transformer. As we said, Y is a predicted action probabilities based on the input X to the network. And we said that everything is differentiable. So if we can somehow backpropagate through Y, we will definitely also backpropagate through FL. So we can also train our length estimator network. So what can we do here? The point here is that, again, like the previous work, Here we use some masking technique. But how can we create our masks here? In the previous work, we knew the order of actions and we knew the length of each action. So we had this position and the length, and we could easily generate masks. Here, we don't have the order of actions, so it's not that easy. However, we know that Y is a probability tensor. So we can use these probabilities as some masks for our network. How can we do that? We know that there are M actions happening in the video during this training, and M is the cardinality of the set we have. So we select those. What we do here is that we have this Y T by C tensor, and we select this action from here, from the C side in the tensor, from the C dimension, and we will get a tensor which would be T by M. And if we transpose it, we'll get this tensor, which looks like this. What does it mean? It says that if we have, for example, action A, A1, action A, for example, I call it 3, and action A, K. So by A hat, I mean that we know that it's in the supervision. So by selecting this, but if I look at this transpose W matrix, I will see that here, for example, action A, I have a tensor which the size is T, and the values are between 0 and 1 because they are coming from a probability tensor. And in the regions that that action is available, the values are higher, tending to be 1. The regions that that action is not available, they should be 0 or tending to be low. So having this, I have a mask for set of actions that are available in the video. And this mask has somehow the location of the actions and also the length of the actions. And where are these locations and lengths coming from? They are coming from our action prediction head, which predicted A, and also length estimator network, which predicted L for us. So if I, having this, I can say that I have the mask tensor here. And if you remember, we also had an intermediate representation. We were calling it Z, which the temporal dimension is smaller than T, but it's higher than Z prime, which we had these K regions. So it somehow is in a shallower layer of the network. So it has higher temporal resolution, but lower contextual information. We use a classifier network here, which is a convolutional layer, to represent this network to first T prime by C. So we have the action probabilities, and then we do a simple linear interpolation to get it to T by C. So we have this intermediate representation called S, which has higher temporal resolution, but lower contextual information because it's in a shallower layer. And we have these masks, which they have more contextual information in them, and they also have some temporal information from this length estimator. If we multiply this mask to this S tensor and just normalize it by T, what we will get? We will get V. How? So I write the equation here. W is a matrix which is M by T, and S is a matrix which is T by C. So if I multiply them, I will get a matrix which is M by C. And by M by C is the V, We call it V, and it's a set of predicted actions. We have M actions and tensors, which each of them has C elements. So yeah, they are the probabilities of the actions. And having it, I already also had the A hat, which is also M by C. I can have the loss here, and we call it the self-supervision loss here. And we use this sort of consistency in different level of representation as a supervision signal here. And we also solve the problem of that not having the order of actions. And yeah, this is the overall schema of the proposed network. So during the training, we have all of it. And we use this transformation and all of these extra losses and regularizers here. And during the inference, we just use this part. And we feed the data to the network, and then we get the action probabilities. So what are the effects of the different losses and regularizers we have used here? As you can see, if we just use the LS, it's not doing somehow nothing, because on this data set, by just a random prediction, you can get somehow 7% or more. And then, as you can see, just growingly adding them, we can get better results. However, we get the highest results when we have our transformer involved here and here. And we have also tried, instead of using this transformation technique, using some KL divergence technique to see what if we just using KL divergence to the just compare the Y to the S without also using the A hat. And we can get this result without the LT. But as you can see, that our transformation has a superiority to the other available losses of techniques. And you can see the results. Actually, this type of temporal set supervised temporal action segmentation is a little bit quite new. The related work, the only related work which was working on this was from CPR 2018, again from our group. And there are two new works in CPR 2020. One of this is from our group, another is from another group. And yeah, you can also check the paper. They're using another technique. So yeah, as you can see, we have improved a lot on the state of the art paper. And so let's see some qualitative results of yeah, it is somehow in fast mode. As you can see, this is our prediction. This is the ground truth. So this green part is background. And then this action, the blue one, the moment is a spoon powder, which we have predicted it right. Here, we have predicted the background. Somehow it's right, but in the ground truth, it was not background. But yeah. And yeah, you can see. So as you can see, it's not a really easy task because even the videos are too hard for these artificial neural networks for processing them. Because, for example, in a data set like, okay, would you please get out? Hello. Sorry, there's a problem here with my not getting out.
Can you click back? Just get back
Working.
to the previous one.
I'm trying, but I don't know what has happened to.
Press backspace, escape.
Yeah, it's not responding.
Not responding? It's
No,
odd.
here. Um,
Should probably stop sharing the
yeah,
screen.
if you can do it for me, because at the moment I don't know why it's not.
Doesn't, let me
No,
see.
no.
Um, see if I, no, I can't.
You can. You also okay
No, I
here.
can't um remove this presentation because I'm not.
Okay. There's a problem with Google Meet, I guess, because it's I can switch to other windows on my
Can you
laptop, but
close that? Can you close the tab?
let me. So
Okay,
did I?
no.
Okay, so the sharing is a stop, right?
Yeah, the sharing
Yeah,
the
but
screen is
yeah, this tab is not is really okay.
that didn't
Weird.
help.
No, I have to close my browser and reopen it and then join you again because I have no other option. It's not. Yeah,
I do we
please.
have the
Oh, yeah,
take?
yeah, 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 yeah. Now it's working.
I don't know.
Yeah. So now it's working. Okay.
Okay,
So yeah,
good.
can you see me?
I do see you, but I don't see the screen.
Yeah, actually, it was the last slide,
Okay.
and now it's time for questions. There.
Oh, sure. Yeah. Okay. So thank you, Mohsen. It was really
Thank you.
great. I know that sort of thing is not easy. So handling a large amount of video data is hard, and applying deep learning, that sort of approaches, getting results is very time consuming, and it requires knowledge and skill. So you have done a great job. I really enjoyed it. So I have a number of questions for you. So one is that I'm asking from the YouTube chat. So somebody asks, in the weak supervision, how do you get the order of actions from the transcripts? Is it some sort of text segmentation followed by summarization? So they wondered about how did you um,
For
how you
for
generate
they
it?
mean for the version that we have the ordered sequences of actions, the transcript, right?
Right, yeah.
Actually, for the data sets, in terms of
They
just
already have that.
yeah, they already have. But
I see.
in real world, I think for uh, but the first paper they had, the authors of the dataset paper, they had suggested just all the same technique, just using some text summarization techniques.
Mhm,
For example, extracting the verbs out of the transcript of the
mhm,
actual subtitles of the movies,
mhm.
and then getting these ordered sequences. Yeah.
And there's another question asking about the output of i3D. So is
Uh-huh.
it so for every frame you have some dimension output features, right?
Yes, for each, for example, i3D is 20, if I'm not wrong, it's 2048,
Hmm.
the output dimension we get.
Okay, I
And
see.
yeah, this is just representing the frame. And uh,
So does i3D has temporal subsampling? Does it
yes,
have?
it has some temporal, some sampling. It depends on the data set. For example, some of the data sets have already downsampled the they put the videos. You
Uh-huh.
know, the frame rate is low. If
Hmm.
I'm right, I think the breakfast is a 15 FPS.
Hmm.
It's not 25 or 30,
I
and
see.
some not. And it depends. So you should somehow adjust it to the type of video you have. And actually, this is an open problem in short video understanding
Hmm.
community, like the 3D CNN, that still people are trying to solve it to have some adaptive frame rate as inside or outside the network. But yeah, you should, for example, for I think for breakfast, we didn't downsample it because the data is already downsampled. But for not these data sets are not for this work. They are for from my other research, which are on streamed videos. For example, on kinetics, usually, for example, the slow fast network has the temporal steroid of 2 and gets the 32 frames as the input. But the X3D network, which is CPR 2020, for example, the X3D is small. They are if I'm right, they're getting 13 frames, and the temporal stride is 8. And they have really they have lots of ablation in the X3D network paper about the effect of this temporal stride and the temporal sampling they are doing, and people can use. And for example, for something data set, it's totally different. For example, a slow fast which works with 32 frames with a stride of 2 on kinetics, they change it to a stride of 2 but 64 frames, or in something video data set. So this is.
But here in this work, the I3D, does it have temporal stride?
For the breakfast, the temporal stride, if I remember it right, it's the temporal stride, I think, is 2,
Okay.
but the temporal window is, I think, 20. Yeah.
And back to the part that you were explaining your model. So I have a question. Is the number of predicted regions, is it always fixed? So you
It's
always
not
have the
fixed
fixed number.
because we have a fully convolutional architecture. It depends on the input video.
Mhm.
It is a fraction of the input video.
But so it depends on the total number of input frames.
Yes.
Okay,
If the video is too large, then we will get lots of regions. If the video is
regions.
smaller, then we will have less regions.
But for a fixed length, for the fixed length videos, it's always predicting a fixed number of regions, right?
Yes, yes.
Okay. And then the other, I think this is gonna be, yeah, the last question is, um, so in the predicted, the output of one of the outputs of the network, you have capital A. So capital A and capital L, right? So the set of
Maybe I can
actions.
show the slides. So you might see my screen now. Uh, Can you see my
Yeah,
screen? Okay.
I do.
So
Oh, great.
for
So if you
let's
go
me
to
this one,
that one, yeah, yeah, that one is good. So capital A is
capital A is
yeah.
the
So you see
predicted
A and L,
action.
right?
Yeah,
So
capital
is
A
it
is, yeah,
okay? So A, is it? I assume it's always ordered, right?
A is ordered. Yes,
Okay.
this is one of
So
the problems that we are solving in this transformer here, because
I see.
everything we have in the network is ordered, but
I see.
the labels are not ordered,
I see.
and
Okay.
that's
So
how we saw. Yeah,
the
for
that one SCT is actually the role is to kind of impose this unorderedness onto the predicted outputs.
the SCT. Yes, exactly.
Yeah,
It's
I see.
transforming an ordered temporal sequence to an unordered set. This is
I see.
this transformation. What is it doing?
Okay, that makes sense. Oh, that's great. So
And the point
uh,
is that sorry for interrupting you, is that we are doing it by also somehow trying to enforce this temporal length estimations we have by applying the mask.
mhm.
Yeah.
Yeah, I get that. Great. Okay, so thank you very much, Mohsen, for this
Welcome.
great presentation. I really enjoyed.
It was my pleasure.
Um, Thank you. Thanks. I would like to thank the audience for joining us. Hope to see you all in the next presentation. Have a good day.
Okay, have a nice day. Bye.
Goodbye.